He's very chatty. You'll make notice of things that are in your mind, but other presenters might not.
You guys are ready? We start with the next talk?
Yeah.
So that's the second talk for tonight. It's about the code will be in Scala. Okay, language of choice is Scala. So I don't know how many of you are familiar or not with Scala. This is like a dictionary, it's a map. Okay, these are keys and strings, and in this example, these are like lists as value of this map. Okay, makes sense, right? Yeah. So a map is basically a set of key values. Okay. Now, why I'm bringing this up? Because if you look at your code base, in whatever language you're writing, you find some place that somebody made something like at least 4 levels deep in nesting, okay? Okay, in this scenario, it's something very simple, but if I can tell you what actually we found like in our code base a couple of years ago, when actually I thought about this presentation, we had something like this, but instead of lists, we had maybe binaries of probabilistic like data structure. It was like, yeah, crazy stuff, or sketches that we had to do what? So basically every time we were opening one layer, there was always another layer, and another layer, and another layer. Okay? Whoa. That's pretty cool. Now, specifically, when I thought about this talk, I was doing a code review about an operation that was happening multiple times per second between 2 different instances, like of nested maps. This is a simplified version, okay? But think about a 4 levels deep map with all the craziness of keys and values, okay? And here I simplified just to give you an idea. Now, if you think about these question marks here, how many possible implementations you can do? Like, think about it. If you think about, like, okay, I need to merge. That's the point of this talk is, how can we merge these kind of complex data structures? We need to try to peel one layer at a time this map and do some logic, and depending on which level we are, with our logic, we have to do an operation or another. So I was doing this code review and I was like, hold on a second. This guy made so much code. Like there was like so much code everywhere. Of course, 0 unit tests, 0 unit tests, but the problem is this, that if you change something, you know, especially even in Scala, you know, doesn't help if you don't have like unit tests with this kind of logic. You need some sort of like safety net that if you change something, you want to have the guarantee that you're not breaking the whole thing, right? So there was a lot of code, a lot of implementation for that code. And what we're going to do tonight is something more fun. It's about something more interesting. We just blend things. Okay, so what we want here is just, you know what, I want this instance, that instance into a blender, and want to press a button and have them smashed together. And we're going to talk about this in a second. But before that, let's look at 3 data structures that we're going to use tonight, 3 collections from the Scala world. Okay, these are the 3 abstract types. So basically, sequence is, as you can imagine, it's like a list, okay? Values one after the other one. Set is like a bunch, like a group of values. And map, as we have seen like minutes ago, is basically a set of key values, okay? These are the only 3 things that we're going to check out tonight. And one thing about Scala, and that one of the reasons why I used this language for this talk, is that these 3 are basically these 3 are abstract. These 3 things are traits, okay? And Scala, the standard library, gives you immutable implementation and mutable implementation. Why? Because when I was talking with that guy back then, like 2 years ago, we discussed a lot about mutability and mutability, and there's no surprises when I tell you that I believe that mutability is an optimization, okay? And there was a big argument with that guy. But anyway, it's fine. This is fine. So again, Scala has 2 different implementations, and we're going to check it out tonight. But the point is, as I promised you, I want to blend things. But blend, it's a very generic term, and what the hell is going on here? So it's a very generic term, like what that means, blending maps and this and that. I don't know, I'm just making this up. So let's find a common ground. So let's say that when I'm blending list, by the way, a sequence is also traversable in the scalar world. And traversable has this plus operator. So I suspect that when I say blend, I really need this plus operator. As you can think, like you can expect from list, plus will be the concatenation thing, right? So if we have two lists like this, list 1, 2, 3, and 4, 5, 6, what you're expecting for this plus is to append one list to the other one, like concatenate that, okay? So far, so good. So probably when I say blending, I mean in the list context, I mean concatenation. Let's look at the other data structure. So let's look at set. Again, it's a traversable as well. You can traverse a set. Traverse has the plus operator. From the API, it should be called addition. Anyway, we have two sets with plus then. We blend them, okay? We add them. So basically, we're going to have a set that contains all the elements from both sets. That's very easy, right? So far, we don't step up again. And of course, if we have a common element from the two sets, we have no repetition because sets is a set of distinct elements. Okay? Everything's super easy here. We have a black phone. We throw the black phone, dark gray phone, or into the blender. We press the button, and we get dark ashes. Ooh. Questions?
Right here.
By the way, anytime you interrupt me, it's fine.
Say the set is traversable?
Traversable, yes.
It is? But I thought sets didn't have order.
Traversable is a property that doesn't need order. That means you can traverse even map.
Kind of like iterable.
It's like
so you can iterate over each one, but it's not guaranteed what
order will come out.
The order is not guaranteed, yes. So check this out. Check this out. The order here is not maintained.
Oh, interesting.
But it's traversable. You can traverse this set,
Okay.
this set, and this set.
Clears it up.
Yeah, that's a good question. If I don't know the answer, somebody else maybe has the answer. That's a good question, actually. And if there's something strange in the Scala syntax, please interrupt, okay? Especially when we get into the functional side. So we are at this point. Everything is super easy, smooth sail.
Cool.
Now, let's get map. Map is, let's say, a set of value, key value pairs. Okay? So again, from the doc, we have, you can find like references everywhere, okay? I'm gonna publish these slides if you're interested to see, you can find references everywhere. So this is adding again like sets. Empty map, map with one element, map with one element. But now, let's put these two guys in the blender, and let's try to blend them with the plus from. So basically, if we have the same key, but two different sets, what's going to happen? I mean, how the API how this API has been implemented by the Scala guys. So, in other words, I thought about 5 different options. Could be this set, the set merged together, a random exception, or a compiler error. Now, a question for you: who believes is in the first 3 the real answer?
I mean, it depends on what you're trying to do.
Just running this command.
Right, but I mean, it depends on what you intend for that command to do, right?
It's typing ++, and I'm expecting, if I do this in a console, what's going to happen? Does it compile or not? Or who believes either is an exception or a compiler error?
Could you clarify the
Sure.
meaning of plus, and also is there also just this plus operator?
Yes, I can actually do that, probably doing this. So if I do type ++,
You use the size.
oh sure, of course, this is
Thank you.
not Haskell, so I
But we want to see the error.
okay, forget about it. I don't know how to do it in Scala. I forgot. I'm using. By the way, so what is ++? So basically, that was the question, right? Plus plus is a method on this abstract class. So these three are abstract classes extending traversable. So basically, these in this color are implementations. So these are real classes. These are abstract ones. Thing is, traversable has a definition for plus plus. Then the concrete implementations, actually the implementation is at this level, are implementing here that plus plus. That's the main point, is that depending on which abstract class we're using, we have a different implementation. For set and map is an addition. For sequence is a concatenation. So this is the meaning of plus plus. So it's a tricky question, and it compiles. Why it compiles? Because this map is a map from a string to a set of int, and this is a map from a string to a set of int. And plus plus, if you look at the signature, is expecting two things at the same time. So it compiles. But which one is the implementation? It's very hard.
It's got to be two.
But it depends.
Could be any of them. They're all plausible.
Yeah.
Exactly. It depends on that guy who implemented that thing. And that guy was not very nice with us, because the definition of plus plus, to answer your question again, for set and for map is exactly the same. It's like, if you look at the doc, Scala doc, it's exactly the same. That means, I don't know, I have to try it out. And if you try it out, it's a third one.
That's right.
So basically, no matter what you have here, you just get the last one. So the one on the right that's most is going to be overriding it. Okay?
So you're saying in general it's not going to recurse into the plus plus instance on sets?
Yeah, and all, of course. That's the main, the core part of the talk.
But there are times when you want to do that.
I want to do that. This is what I want. I want something, some magic here that gives me that. This is what I want. I don't want this gray shit. When I put the iPhone there, I want this. That's the point. This is the talk.
So, Filippo, would you expect if you had two sets of maps and you tried to play them, that you would also, you've got, hang on, does that make sense?
Then it's going to use equality to check them out. It's fucked up. Sorry, I'm saying bad words here, but it's you know what I mean?
Yeah.
But if you stop for a second and think about it, it's like, I want that.
Yeah.
You want this.
Yeah.
Well, sometimes you want that, sometimes you want the other.
Why don't you want 4 or 5?
Say it again?
Why don't you want 4 or 5?
That's a good point. Guys, oh no, for 5 no, because there's nothing here.
Well, I'd rather have 5 than 4.
At the end of this talk, I can show you, we can actually talk about it. We can talk about it, that we can have all those 3 options, depending on what we want, okay?
I think compiler error is almost impossible without dependent types or something weird, right?
Yeah. Okay, so this is what we want. We want the rainbow. I want the rainbow, okay? So now, I want to implement the blend that does the rainbow. So what that means, if I have a collision on the keys, this is what I want. I want a logic that basically does plus plus. Done. Now, how that logic looks. So if you're new to Scala, this is a signature. This is the return type. So we have one map, strings on the key, and a set of int on the values, okay? Next map is the same one, and then this is the return type.
So just to kind of deconstruct that a little bit,
Sure.
the signature, the annotations in Scala, it does it within the arguments.
There's a comma here, very
the
tiny.
inputs. Right.
This is one argument.
Yeah.
This is another argument.
It takes it within the argument for the arguments, but it's on a separate line. The output, the colon map is the output annotation. Take the return.
It wasn't too long. The line was
Oh,
longer.
that's one long line.
Yeah.
Okay. Yeah. I'm trying to distinguish in Haskell. You put the type signature on one line, and then the.
Yeah, I know what you mean. Yes. No,
I
this is
don't know about
just the
this
definition.
complex
This is just the first line. Say it again.
I don't know about this complex ivory tower stuff. I don't know why they can't just use practical, simple Haskell terminology.
I know. That's what I think.
Okay, so this is the signature we actually going to try to use as blend. This blend, let's see in this world where I'm talking about, there's many worlds, okay, in this universe. In this world, this is how blend looks like. Now, let's do that. For each, if you're not familiar, you have a map, and for every element of the map, we're doing something, okay? We get every key and value, and we do something. Why I'm doing this? Because I want to shoot in my food, okay? Yeah, that's the main reason. I'm doing this, as soon as I do this first step, it's so, I'm not saying it's wrong, sorry, I'm trying to be more objective.
You've made it more difficult than it needs to be.
I'm introducing mutability. As soon as I do this first step, unless you want to find another way, you just tell me how to do it because it's not possible, I'm introducing mutability. So some side effect must happen in here that is not observable from outside unless it's mutable.
So for each in Scala is the traditional one where either it does nothing or it mutates. As in you can't for each can't like do immutable things. It just sits there and runs a bunch of things and then you never deal with the return.
Correct. So when you run for each, the return type of for each is nothing. Okay. That's a very good question. That's the main difference. If it was, let's say, a map, here we go. We have a whiteboard. Let's use it. So if we have a map, we have a bunch of elements. If we map them, we get like balls. Okay, I'm gonna map from square to ball. Okay? Just make it up. Yeah. With for each, there's nothing here. So from this, you go to nothing. Okay, so you must do something inside that modifies the world outside. So this is what I mean when I say that.
So why did you pick for each?
Because we're going to do the mutable implementation, and we're going to add the result map, okay? We're going to create a mutable map. So this, by default in Scala, is immutable. You must specify it. So I'm going to create a mutable result map that I'm going to return here. Okay, this is just plumbing. So basically what I'm doing, I'm getting this map MA, I'm making that mutable, and I'm going to do some side effects here, and I'm going to return the immutable version of the map. So this is immutable, okay?
So that first line with val result, where you're doing the plus plus operator, that's basically just to clone MA as a mutable map?
This is one way to create a mutable map.
Okay.
Yes, so it's just plumbing. Okay? Now we have the result. Which kind of logic we can use here? For every element of B, if the key exists, we're going to merge them together. Okay? We change the, that's mutability. We modify, very common in Python, right? We modify the dictionary in Python all the time. Here, we modify the map, or in this scenario where the key is not inside of our result, we just add the key value, done. This means, in Scala, means it's a comma. It's just a funny way to show a comma. Okay? Too much Scala code? There's more. So now we have on the left the mutable version. Let's do the immutable one. Okay? So mutable version, immutable one. Okay, there's a lot of code, just focus on this. This code is exactly the same. Instead of mutating in place, we're going to create a new map adding these elements. So the logic is exactly the same as you can see, okay? I'm just creating a new map instead of modifying place. In order to do that, I'm going to move from for each to what? This cryptic thing, okay? This is a fold left. I don't know if you guys are familiar with fold. Fold is something simple as a high-order function, basically. So you pass a function, and then you ask the fold, oh, you know what? Could you please, for every element, call this function, but you also have a state. You can call that 0, seed, whatever you want to call it. In this scenario, the seed is MA, so we're going to pass the first map, okay? That will be called result, like that, okay? So we have a result. For every element, for every key value of B, we're gonna, iterate through all of them, running the same code we did in the mutable version.
People are used to languages like Ruby, Python, or JavaScript. Fold is also called reduce.
Yeah, what was throwing me for a second
Sure.
is it was a binary operator that, and the MA is basically a conditional condition.
MA is the, do you remember two maps?
In the slash colon.
Irreversible.
Okay, I'm gonna show you
I
this.
would have thought a fold is like, there's only one thing you fold, not two arguments to it. But it's a conditional
You've got the
condition.
starting element.
Yeah.
You can have the seed.
Yeah.
If not, otherwise, with reduce, you should have no seed, and the seed will be the first element. But this is at least in Scala.
Yeah, except Python cheats.
Exactly.
And Ruby and JavaScript all cheat.
Please tell me that fold right is just using the opposite slash.
So, fold right? No.
Come on.
Yes, it does.
Is it? Okay,
Because it's for the domino. So the idea is this.
Ah.
So this is the seed. This is the seed, and you're going through all the elements.
Now it makes sense.
Yeah, it's using that.
And it's unbelievable. As soon as you see this, you never make a mistake on that.
No.
But people get that. People get that from other views.
Now I get it.
bad.
Incredible.
Yeah.
I think fold left is also useful.
But then you don't get the little
So,
Okay. Complaint number one for Scala. Complaint number one is the syntax. People get nuts about this stuff.
Yeah.
You just need to learn. I'm sorry about that.
MA is slightly based on the.
That's kind of like a.
Okay. Now, because we're in the immutable world, and because I'm old, I cannot have my cognitive. I cannot have mutability. It's too heavy on my brain. So now that it's immutable, I can actually refactor it safely. Okay. You can, if you're good with mutability, do it in a mutable world. I'm not good enough. Okay. And when you get used to mutable data, you kind of forget how to use mutable data in a sensible way. That's in my case. Okay. So what's happening here? These two guys are exactly the same. We're gonna get them outside the if. Okay. And this tuple, there's a one-liner you can do in Scala. You can do get, and at the same time you can get the thing. It's called option monad or maybe monad. You can get the thing or none. It's easy to show you. So basically, I took this outside if, and then with this one-liner, I'm gonna get the value by the key or nothing. So in case there's the value already, the key and the value are already there, I'm going to concatenate them. I'm going to plus them. Otherwise, I'm going to create a new key value. Okay? Nice one-liner. And now, of course, there are at least 4 ways to do it in Scala. Okay? You can reduce this in one of these. Now, because when I wrote this slide, I was reading
Such an excellent paper.
this one. Yeah. I read this probably 20 times. I still don't fully get it, but I say, oh, fuck it. Let's use a catamorphism because I'm a hipster and because it's the shortest version. Okay. So kata is a catamorphism. Basically, you have it's a fold at the end of the day. But anyway, long story short, this is the same as this, and this is the V. Okay. It's just a one line. We can talk about this later. Anyway, at the end of the story, these are the 2 implementations. Okay. One is the immutable and one is the mutable. Very, very, very similar. One with side effects on result, one without.
Is the underscore plus plus just creating an anonymous function?
That is correct. Sorry, I forgot to mention. Underscore is the first underscore is the first variable, argument of the
So if you
function.
create an expression with underscores, it just magics it into a lambda?
Yes.
That's interesting.
Section in Haskell.
So in Haskell will be /x.
Well, but yeah, you could just have like plus plus v as a section in Haskell, and I think you do the same thing.
Yes, because will be because of curry there. Right?
They're all going to be
Plus v will be the other way around. You need to flip it.
Or you do plus plus v or v plus plus, I don't know, the section is by the way.
The underscore itself, that's no arguments.
This one.
Yeah.
This is an anonymous function. So if you go back 1 second, Thank you for the question. Let's look at the first implementation. That's the easiest one, okay? So we get from the result, so what we have right now, our state, we get the key value using the key, and then if we have a value, okay, we map on it, if we have a value, we're going to concatenate that value with the actual value, t, that we got from.
I'm
So it's
still
kind of
confused. In
complicated.
some languages, in anonymous functions, an underscore represents
The
an
argument.
empty argument list. Is that what it represents here?
No, these represent the first argument. If I had 2 underscores, that means 2 arguments. The first underscore is the first argument, the second underscore is the second argument.
Okay.
But that's not very important to understand the whole thing. The point is that, we have those implementations. One is actually implicit, in our function, we explicitly show that the result is going to get passed over and over and over in the default. In the other case, we're just doing shit to it. So again?
I was just doing shit to it.
So,
A thing happened.
Just don't look
this
at
is
it
so
as a-
Python. I'm doing this in Python every day.
Oh, yeah.
Out of curiosity, is there a major performance difference between?
I'm very glad you asked. I have bonus slides at the very end. I'm going to show you the benchmarks. Ding! Thank you. I have the benchmarks. Now, that was easy. Let's say somebody again is going to say, oh, you know what? Instead of a set, I want a list, or instead of a list, instead of a set, I want a map from integer to set of integer. What are you going to do? You're going to change the signature, bigger. Again, you see the pattern here, okay? From one type to the same type, returning the same type. Fine. What's implementation? It's going to be something like this, plus blah, 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 nested, complication, logic. Fine. That's the normal way, okay? You do it, and you find. Let's try to abstract. Okay? This is a type class. We can make just a talk about type class. But in this scenario, you can think about an abstract class that is, you can parameterize it with a type. So you put a type, so I'm going to show you in a second how, but you're going to pass a type A, and you know that you can implement a blend function with that A. Okay? So something that in my world is blendable I should implement something with this signature. I'm going to explain this in a second.
It's the same thing as a semigroup.
Ah, don't worry. Yeah. So basically what I'm doing here, let's forget about semigroup, let's talk about ad hoc polymorphism. So for every type I'm passing, I can specify the type, I don't know, integer. And I say, oh, you know what? I'm going to blend these 2 integer, returning an integer with this logic, okay? With ad hoc polymorphism, with many languages, with either kind of type, I think you need to ad hoc polymorphism, right? So you can do also with C++.
All you
Yeah.
just need is just not having any types, like Python, and it's fine.
So, yeah, exactly. So, the point is, now that we have this kind of stuff, like this kind of abstraction, I think we should step back a second.
Can I ask a question on
Sure.
the previous slide? Rick?
Sure.
The trait keyword, that's what introduces or defines the polymorphic type?
Okay, yes. So basically, this trait means, you know what? I have an abstract class blendable that has a type parameter here. So if you want to use blendable like here, like new blendable, you must specify a type. Or if you don't specify a type, you're going to specify something outside that is going to specify a type. But you need to pass a type here. This is basically a type class. So in other words, you're saying, in my world, I define something blendable for whatever type if I have a function blend that I pass 2 things of the same type, and I get another thing of the same
What
type
I'm getting
there.
at is the keyword trait. That is the mechanism in Scala to create a type class?
Yes, that is correct, yes.
Okay.
That's one way that I know, yeah.
Okay.
You can do, depends on the trait, it depends on the type class. You can also have case class if you want. I don't know, anyway, yes, this is the main way we do it. So, step back a second. Let's think about what this blendable thing and keep talking, I keep blathering about it. So what I really want in my world. So as I mentioned, in my world, when I want to blend two lists, I want the plus plus operator, okay? I want to concatenate them. With set, I want to add them, okay? So for list is the plus plus, for set is the plus plus. But in my world, let's say in this world, if I have two integers, what I want to do when I want to blend them? 1 and 2. We could, I don't know, multiply them. In my world, this world, I want to sum them. Because I say so, okay? You can have another world, you can multiply them, okay? But the important thing is that I have type and an operation plus. Strings. How many things you can do with string? When you blend string, I don't know, maybe you want to burn everything and just keep the first digit. I don't know, that's fine. That's a way to blend them. But in my world right now, I decide plus. Concatenation, string concatenation. It's an arbitrary decision, okay? But you see the pattern here. We have a type. This is the blendable. We did everything wrong. We could blend, okay? And we have an operation.
Are you expecting blendable to follow any particular laws? Or
Yes.
Completely out?
Yes. And this is where you mentioned laws. You mentioned laws. Yes. This is where our mathematician friends are coming in to help. We saw these patterns. This stuff is pretty simple. It's pretty simple because it's algebra, okay? So be careful. So there will be some algebra. We all of us, we studied this in high school, but we forgot about that because we thought it was useless, okay? Yes. Crazy, right? Yeah. All the time. We're gonna see one thing tonight. That's the only slide about math tonight. That's it. It will be a funny night tonight. Very easy, you know, work school night. So, what's a semigroup? The one that you just mentioned. Semigroup is a set S with an associative binary operation. That sounds very cryptic, okay? Sounds very, very cryptic, but honestly, this is way more cryptic. So this is one thing. Well, vending machine that has credit card only, debit card only, cash only. Paying with cash or credit, no cash accepted.
Oh, wow.
This is cryptic. The definition before is not, okay? This is cryptic. Also, you also have RFID.
Yeah.
So
Okay.
cryptic, it tells you exactly what you can do, which is everything and nothing.
Exactly. So I think it's a Schrödinger vending machine. I don't know. Anyway, I don't know.
You stop looking at it, it goes away.
So that one is not cryptic. The first part, remember the S? So basically, it's called the closure property. What it means. What we've done earlier on with the blendable and the blend, it's basically, we can create a type class called semigroup. Actually, this is how it's defined in Scala Z. So basically, the closure property says that for every A and B in T, okay, the result of the operation A, operation B is also in T. Scala has a type system, despite other languages. It has a type system, and the type system makes sure that this property is ensured. So all we need to do if you want a semigroup, we have to write code something like that, so like a type class. What that means, it means that if we pass two booleans and we return a boolean in an operation, fine, compiles, works. If you try to do like two integer and return a boolean, doesn't even compile, okay? So the property, the closure property, is the type system that makes sure we have that, okay? The second part of the definition was about the binary associative operation. Okay, here we have a little problem. What is that property? It's basically that if we have A of B of C, you can have parentheses in A and B or in B and C. It doesn't really matter, okay? You cannot flip things. It's not commutative. It's associative, okay? You cannot flip things around, but you can put parentheses where you want.
Does Scala have any way to type check that?
That's a very good question. The answer is no, but we're not primitive. We have quick check, like Scala check. We have property testing just for that. Thank you for asking.
Are there languages where you can write types that will check for things like commutativity?
For example, for Python, sorry, I keep pointing at you when I say Python, but But no, there's a theorem. It's a property based. It's like quick check, but it's not that great. It does.
Well, I mean, quick check is fine for testing, but I mean, is there a type system that will let you assert this is commutative?
And this is where Mark is going to answer the question, right? No, I don't know if somebody has the answer. I do not have the answer to this question.
It's an interesting question.
Yeah, like in Haskell, you can make like these comments, but then it's quick
Well,
check
even,
again.
yeah, even in Haskell, it's something you verify. It's not something that you prove. If you know what I mean. It's just you test it out.
If you're not familiar with the quick check or Scala check or this kind of property testing, I'm going to show you a slide that, well, hold on your pants, Colin. There will be a very interesting slide. So now that we check those properties, if we look at the definition again, it should be pretty straightforward, okay? A semigroup is a set S, okay, the closure property, together with an associative binary operation, the parenthesis thing, okay? SS. That's it. This is a semigroup, those two properties. Done. Now, this is what the mathematician told us. Let's see how is the implementation in Scala. This is the Scala Z, Scala Z, the typoclassopedia. And tonight we're going to just look at semigroup. There's plenty of interesting things. Functor, functors, reversible, monad plus, monad, arrows. There's a lot of stuff interesting. And please, if somebody wants to do a talk about other parts of this diagram, please. Okay, comonad, there's plenty of stuff. Tonight we're just going to talk about this tiny little bit up here. So, what you get with Scala, you get that thing. So you get the context. Let's say, for example, if we import standard set, we're going to get this law. That's the law you were asking for. This law, I read this with you, okay? Set semigroup, okay? It's a semigroup for set of A. That's the other thing you can do with type classes. You can have this A specified here, so you're gonna delegate outside to specify this A. By the way, when you have a set of A, the same A is here, we are saying that we are forming a semigroup for set of A, doing what? We get A, we get B, using plus plus. So this is in Scala Z. So the Scala Z definition is the same one as in my world. So the semigroup of set is basically the plus plus operator with set. This is what it means. Okay, set and plus plus. Okay, that's the operation, and this is the implementation. So all I have to do is just import that, and if I do, if we're going to use the operation, we're going to see that in a second. You're going to have the right now. We're going to have the plus plus. So if I'm going to do sec1 2, this symbol 2 3, we're going to get what we want. Why? Because the implementation. So what we're importing here are the laws of my world for set and for lists. Now, this symbol is called the TIE Fighter symbol because we're talking TIE Fighter. But it's basically the semigroup op. The semigroup operation that mathematicians call them with a dot, the center dot. In Scala Z is like that. In Haskell is lighter spaceship. Yeah, maybe, yeah.
Spikes also.
So what's the difference between the semigroup operator and the plus plus operator we saw earlier?
Yeah, so basically when you call this, you call the implementation call this. So the difference here is that you have an implicit in the context. Or you say, so here you're saying, oh, could you please opt these two semigroups? The implementation that you have by default, you can change it. But the one that you have by default is plus plus.
So
but you can change it.
That pipe plus pipe semigroup operator is whatever is defined in this
In the context. Yes.
type set. Type.
Yes. I need to go back a second, sorry. Again,
Whereas the plus
this
plus,
is my world.
yeah, but whereas plus plus is built into the language of the
Yes,
library.
yes.
Okay.
That's the
So
default.
it's
But you
more
can change it.
generic.
Yes.
Okay.
It's, yeah, probably common sense, but you can change it. So in my world, set is plus plus. But you can, in your world, you can change in that world, could be something else. Like the first set. Return the first set all the time, or the last set. Let's move on. So, okay, that's pretty clear. Same thing. In my world, it's plus plus. Therefore, we have the plus plus behavior. Now, string. The standard behavior. So basically, I specified my world with the standard scala z world. Okay, and we have in this scenario. Same thing with integer. But hold on. I made a trick here, because if you pour the integer has so many definitions. Has, for instance, the max, the mean. So there are multiple operations. Okay, you can choose for integer which operation you want in your semigroup. Now, why I'm doing all this mess? Oh, sorry. Before explaining why, I'm going to answer your question, Colin. This is how scala z is checking that property that the type system cannot check. There is the same group law, okay? Associative, we get an F, and an F. So basically we get those three ops, A, B, C with the op in the middle, okay? He's checking that A with the B and C, B op C in brackets, is equal then AB op C. Okay? This sorcery is working like this. Look, you can type this on the console. I can actually show you the console if you don't trust me. Semigroup close, I'm gonna call this guy, okay? For integer, check. Scala check is creating 100 tests, trying to increase, decrease, trying to find a bug. It's generating unit tests, so 100 unit tests, and it proved, yes, that law holds for those 100 tests.
So this laws, it seems like it's some type of meta thing, is go prove you're consistent with your defined great rules.
What our mathematician friends told us, look, a semigroup is same type, the closure property, and associative property. With the type system, we can always prove the closure property, but not the associative properties. This is one way to prove that, as Colin asked.
So this isn't proving it. This is.
It doesn't find a count.
This is it's doing a unit test.
Trying ways to way how to find it.
Yeah. In a smart way, actually. Yeah.
Is it fuzzing it, or is there a defined unit test? When it says past 100 tests,
Yes.
coming up with 100.
Perfect. It's starting with integer. So it's starting with maybe the smallest integer and the biggest integer, and then it's trying with the 0 and the smallest integer, and then it's trying a random integer.
Those tests are just somehow built into the language?
It's a library.
This is the library called Scala check that is doing that.
Okay.
How crazy is that? How crazy is that? This is awesome. This is one of the best things. And you can do this in Python as well. It's called theorem. You can do the same thing.
Oh, yeah. Hypothesis.
So, hypothesis, sorry. The other way around. Okay, sorry. I'm very excited, as you can tell, because you can check all your guys and you can get a result. We're almost there. Please bear with me for another minute. Now, back to our problem. Do we have an instance of semigroup for our friend? Okay. Here's the cool part. Okay. Some data structures form an interesting semigroups as long as the types of the elements they contain also form a semigroups. This is coming from this great book that I have here. Ooh. Yeah, it's if you type in Scala, it's basically the best book you can find probably now. It's called the Red Book as well. And it's the reference is here. Explain why it's like that. By the way, very quickly, look at this map. We have keys. We have a key conflict here. Okay, there's a clash. Now, if we use the semigroup operator, what's going to happen? In our world, with integer, the operation was plus. So 1 and 2, 1 plus 2. That's pretty intense because that opens. Check out what is opening. This. Yeah. Recursiveness. Tom Selleck recursiveness. Is the most awesome recursiveness you can find in.
That's the best image I've ever seen.
Yeah. Second, there's a picture of it. That's awesome. I was looking forward to use this. Anyway, if you run this with a Scala check, works. And if we have two sets, yay! We get our set. So all this talk just to get there. Okay? So finally we had the rainbows out of the blender. Back to our friend. All we need here is no unit test, no nothing, no implementation, no logic, nothing. You don't have to implement anything. If you're okay with the rule of the word I just mentioned, you just use this operator. If instead of, let's say, concatenation here, instead of like, you know, merging the list in concatenating to each other, you want to do something else, then all you have to do is change the context and create an instance of semigroup for list doing something else, like getting the last element, okay? But if you don't do anything, and that was our case 2 years ago, all I had to do is, the code review is like, forget about that. Import, 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 this. Okay? That's it. If you haven't heard about, you know, my talk, this talk, or anything about semigroup, it should be like magic, right? Okay. So I really hope, like with this talk, you guys found one or two interesting things. Okay? And that's basically what I have for you today. Yeah. Thank you.
Whoa.
That was good, right?
Semigroup magic.
Semigroup magic, and then we. Before getting to question, there's a stuck question about benchmarking. So this is a picture I took like years ago. There was a list with 2 ones. That's exactly benchmarking.
Well, if you hit both of them, you get a back.
I don't know, I haven't tried.
Or 2, it depends on which semigroup.
But every time I do benchmarking, this is so
How do you know
true.
that's not binary?
This is so true. You're right, maybe I'm right, maybe 1/5 of the time. I don't know. It's always amusing to do benchmark. Okay, to answer your question, Colin, I have a cool way to show you benchmarking, and it's this. I don't know if you guys can see.
Whoa.
Okay.
What is this?
What is it? This is a Scala meter. So this is the results of maybe a few hours of testing with different stats. So basically what I used was this map, and then we have different dimensions of the map. Okay. So on the x we have the size. So the size is going this way, and the time is going this way. The lower is the plot, the better, of course. Bigger size, less time, good. So for instance, let's get the mutable naive implementation. The one that we create the result, so from immutable to mutable, back to mutable. It's something like that. This cloud here is the confidence.
Is the x-axis time or memory?
X is the size of the sample.
Sorry, is the y-axis time or memory?
It's time, running time. Oh, that's a very good question. Because time, memory haven't checked.
Okay.
So I'm just looking at time complexity, not space complexity. Not space complexity, time complexity. Okay? That was pretty, you know, it's very easy to beat that, right? So if we do mutable, even with kata, you know, all that boxing, it's not that bad. Like, asymptotically, it's almost the same, okay? But if we look at the immutable way, like the naive one, it's faster. Why? Because we don't have to convert, reconvert, okay? That was very...
Is that just the compiler is smart, or is it the implementation of the library?
I do not know the answer for sure, but I can tell you it's creating and recreating, you know, because we're converting from immutable to mutable, and from mutable to immutable again. It's not, these are 2 completely different data structures. That's why it's taking time. That's my understanding.
Okay.
So the compiler is not that smart. Now, this is the immutable one, and this is the immutable with kata, the katamorphism. Okay, exactly the same. Now, quick question for you. Where the semigroup with all those contexts, in and out, where is scoring? Better, between those, worse, same.
About the same.
About the same of one, of this one or that?
Immutable one.
Immutable one. I would bet the same. I don't remember the result.
I'm going to take a swing and bet that it's fantastically better.
No, how? Okay, I don't know how, but I think it will be a much the same. I don't know. Let's find out. Here we go. Clean. Yeah, it's basically the same.
Yeah.
It's the purple one, so it's basically the same. In other words, we use all those sorcery, and sometimes people say, "Oh, this functional programming is so slow. What are you doing? All this complication for." It's basically the same as the immutable version. Okay. But we have to be honest. Let's look what you have in a fully mutable world, where we trash all the mutable part and we go like full mutable. Faster, but not that fast. Even if we remove this mutable, honestly, I was expecting, it's not that different, right? I mean, there's a lot of noise here, so maybe if you stay like, it's not even
Especially
loud.
once you,
I mean, that's like
especially once you're throwing the copies,
like a
you're going to have to do it.
So, what question at a time?
Well, especially once you're throwing the copies, you're going to have to do because you're not sure what's going to happen when you throw this thing in. You know,
But I mean, that is like 50% worse. So I mean, if you're doing this a crap ton of times, that's gonna get real ugly.
Oh yeah, sure. I mean, first, with just one symbol, you get it correct. And then if you need this, I would suggest you, yes, you go mutable if you need that. I don't know how many times I need that, but if you need that, yes.
Right, I mean, you don't want to perform something that's afraid of it.
Or you can actually change the data structure in the first place.
Did you look at lazy implementations of this?
I did not.
Because I assume, like, if you're taking a large data structure and blending with another large data structure, maybe you don't need all of it all the time, so you get another benefit by just making it lazy.
That's a good point. One thing I didn't mention, the immutable version is creating a new map every time. But because the data, the sharing, basically the new one is sharing almost the whole data of the previous one, and you can see that it's pretty good. I forgot to mention that, yeah. Okay, this is basically all I have. And what else? Oh yeah, of course. Choose once. Okay. Any questions? Yeah.
That semigroup operator, the pipe plus pipe,
Yeah.
how do you read it?
I
What's
would
its
call it
main
semigroup operator, but if somebody knows better than me.
Would be blend?
No, I invented blend. It's a joke for
You
this
invented
presentation.
blend?
No, it's a joke for this presentation.
Oh.
No, don't say blend out of this one. Yeah, it's a good point. It's a good
The
point.
canonical name would be A and B.
Okay, the canonical name, I can tell you the story because I checked it out. Yeah. So when I say canonical, I mean from Haskell, because everybody look at Haskell, and it's called mappen, M-A-P-P-E-N.
Okay.
And it's called like that for a mistake that has been made in the 90s. Yeah, because maybe somebody say, oh yeah, semigroup is just a pending list.
Yeah.
And then they say, yeah, but this is a monoid, because monoid is very similar to the semigroup. Say, oh, I don't want to call it
But it's
a
not
monoid append. Let's call that mappen.
It's not a monoid. It doesn't have an identity.
Exactly. But since then, they use the same thing. Now, semigroup, it's inside GHC, and it's inside like the standard library in Haskell since GHC 8. So it's pretty new, if you think about it. Before that was just experimental on libraries. So was mappen since then. That's why the name. How people is calling it, I would call it semigroup operation because
That's not long.
but the mathematician called that operation. Semigroup. Sorry.
Somebody else.
Yeah.
smart, not TIE fighter.
TIE fighter.
Is there any way to have multiple semigroup operators within the same context?
Yeah, that's a good question.
Because let's say you have two different data types, you want to do that to in a given
Okay, I made a way longer version of this presentation like last year. I have the slides, I need to find, there's multiple ways to do it. So you can have a non-empty list, and you can call sum L1. It's kind of complicated, but anyway, it's sum left 1. Anyway, the point is, yes, you can do that. You can basically put everything in the blender, you press the blender at the end. Yeah, and then it goes actually in parallel if you want, and stuff like that. Is that the question, right?
Kind of. So I mean, you said that you can change the definition of the semigroup operator depending on what you're importing into your local context.
Oh, sorry. I
So
missed
if
the
you want to have multiple different definitions of it in the same expression. So you want to blend these two things, follow this one rule, take the result, and blend them using a different rule.
If it's it's about the type. It's about the type. So if you're telling me that you want to do different semigroup operation on the same type, you must change context, and I don't know if it's possible.
Because like with integers,
Or you have to change type.
of multiplication.
You have to create another type that is exactly so. String, you have to create a new type.
Okay.
It's easy enough to do something like new type here, right?
Yeah, it's easy to do a new type. Yes. So that's the only way. You cannot have in the same expression. You cannot be in two different worlds. That's the point.
So just because like, if simplest case, you're doing integers, sometimes you want to do multiplication, sometimes you want to do addition to your integers, but in the same expression, it's pretty common to want to do multiplication and then addition.
That's a very good point. That's why you import as close as possible to where you call the thing. So in that case that I showed you, this case, we import all the needed import just before calling this monstrosity. Okay? Just before we create a context and then we call the operation.
So you can scope that even down to like a single function.
A single blend.
Okay.
Yeah, you can do that. Yeah. You can see like, let's say, if you have a look at the unit test on Scala Z, Scala Z about this, you can see that every unit test has different context because they test integer with max, integer with mean, integer with, and they also, as far as I remember, like division, it doesn't form a semigroup with integers. Or double, because the precision, there's no operation you can use for double. You know that semigroups are everywhere, but also sometimes are hard to find.
Are there other ways to deal with these kind of recursive data types? So like in a dynamically typed language, you would just write a recursive method that goes through all this and switches based on type. Are there other ways besides semigroups to deal with this kind of problem in a language like Scala?
I think when dynamic language, you're relying on
get the types.
you're just relying on duck typing, right?
Yeah.
So you apply plus to it and it does the right thing somehow.
But I mean, is there a way in Scala to say like, I'm going to take a map of something and then do a case statement based off that type, and then apply different
You can
things
do
to
that.
in recursive.
I wouldn't do it, but you can do that. Yeah. I mean, there's people like you can see code bases with any val. You see that stuff. But if you have a type system that helps you,
Introspection, isn't
But
it?
it's every time you want to do
You have to reflect
you
on
have to
type.
reflect, yes. Existence of.
Dirty.
Or pattern match.
Can you say pattern match from that?
No, I'm talking about you must introspect that, yeah, you can do that. But anyway, this is one way. I'm not saying it's the way. It's one way. So when you see a monoid, it's basically this with the identity.
Well, especially because sometimes you may want to switch what you're doing not based off type, but based off value. I've been in situations, and they're really horrific, where you have two very large data structures, and you want to, combine them in some way, but depending on the value you want
You're talking about stringly typed. So as strings, everything is a string.
Oh no, but no, maybe with integers, depending on it, maybe with other maps, depending on what keys are available, you do different things.
You can also just define the function as complicated as you want and do something extremely monstrous. But
And then track down the person, put that in user.
yeah, don't do that, but you can.
Okay, thanks. Let's finish this 1 second. No, thank you guys. I hope really there was something interesting.
Yeah, I have a semi-group joke.
So what?
I have a semi-group joke, I'll tell.
Oh no. Go ahead.
What? It's in two parts. What's purple in commutes? An abelian gray.
So what's lavender in commutes? An abelian semigroup. Don't get it?